Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. Training is the most complex and difficult challenge of developing humanoid robots. That's because before the training can even begin, you have to build a brain for the robot using artificial intelligence. The level of sophistication of that artificial intelligence then determines how the robot will be trained. So today, using Tesla's Optimus robot as an example, I'll walk you through the basics of a humanoid robot's brain, the training methods that can be used, the current state of training, and based on all that, how I expect the capability and scalability of humanoid robots to progress in the next few years. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. For this video, I'd also like to give a big shout out to Scott Walter. Scott began his journey in robotics 40 years ago as part of his doctoral thesis, and in the past few years, he's made invaluable contributions on X and in interviews on the topic of humanoid robots. As part of my scripting process, Scott helpfully corrected and clarified my understanding of robots. But, as always, any errors in the video are my own. If you're interested in robots, follow Scott on X at GoingBallistic5. Let's begin with a simplified view of a humanoid robot's brain. Much like the human brain has areas devoted to different functions, most humanoid robots and early versions of Optimus used several artificial intelligence models to operate. Let's look at 4 of those potential models. First, there was a perception model trained on data from Optimus robots and Tesla's vehicle fleet that understands the physical world. The perception model fed into AI models for mobility and manipulation. On that note, second, the mobility model managed the robot's gross movements. That model integrated, for example, accelerometer and motor data for actions like walking, balancing, and climbing stairs. Note that the perception and mobility models didn't necessarily have any understanding of what objects are in the world conceptually, but rather just how to navigate and react to them. Third, a manipulation model was used for fine motor movements of the arms and hands, which included, for example, pressure feedback from the fingers. Fourth, Optimus incorporated a multimodal model. By multimodal model, I mean an AI model like ChatGPT that can process language and object information. However, rather than ChatGPT, Tesla instead uses Grok, developed by xAI, which is one of Elon's other companies. The multimodal model allows the robot to respond to verbal, nonverbal, and textual communication from humans and to identify objects. That's so you can tell the robot to, for example, identify grocery items and put them where they belong. Obviously, the use of a multimodal model like Grok isn't a simple cut and paste. It needs to be re-architected to take in the robot's sensor data. But the general idea is to embody the AI so that humans can work with and command humanoid robots intuitively, like they would with another human, which dramatically increases their usability and utility. Moving along, as I said, perception, mobility, manipulation, and multimodal models are potentially what's used for early versions of Optimus and other current humanoid robots. The reason I added those qualifiers is for 2 reasons. First, each humanoid robot manufacturer will likely take a slightly different approach, and the key point is to understand the complexity and functionality requirements for the AI models. Second, because the ultimate goal is to merge all of those AI models into one streamlined and sophisticated end-to-end AI model that controls every input and output of the robot. That's an important breakthrough for solving humanoid robots because it reduces compute and integration bottlenecks between the AI models, increases the speed of decision-making, and therefore reduces latency in the robot, allows for more human-like behavior, and greatly improves the speed and scalability of training. More on that in a moment. Either way, those 4 basic models, or single end-to-end model, allow for several training methods. The first training method is reinforcement learning, where a digital version of the robot is trained in a virtual environment rather than in the real world. That sounds straightforward, but it's difficult because of all the physics, motor inputs and outputs, sensor information, and AI models that have to be loaded into the virtual training environment. If we look at just one of those, the motors, their performance varies depending on factors such as the temperature of the motors and natural variances between motors. So not only does reinforcement learning require exact motor data in a range of conditions, it also requires building in tolerances to allow the software to work reliably in any robot that comes off the manufacturing line. But all that effort is worth it because it allows the robot to train itself in a virtual environment to, for example, walk or dance without suffering any real-world consequences like fall damage. Additionally, it allows the trainers to accelerate development times in two ways. First, the digital twin of the robot can be altered to see the impact of potential hardware changes. Second, it allows the training to be fast-forwarded in ways that can't be done in the physical world. For example, by running thousands of parallel simulations that compress years of trial and error into hours. The second way that the robot can be trained is through motion capture, where the robot is linked to a human that's using a VR headset and motion tracking gloves to teach tasks that require precision or dexterity. The third way that the robot can be trained is through video capture, where the robot is trained by watching videos of humans performing tasks. Fourth, there will be many cases where the robot encounters new objects in the world or objects that it can't discern. In those cases, supervised learning can be used to provide the robot with labeled data. By labeling, I'm referring to adding wording tags to objects in images to differentiate them. Fifth, this isn't really a training method, but it's worth noting that the robot will have innate abilities as a side benefit of its artificial intelligence model or models. That's because artificial intelligence uses huge amounts of data and compute that give rise to pattern recognition and contextual reasoning. And those innate abilities will expand over time as the AI models become more sophisticated, powerful, and have more data to draw from. No training necessary. The next question is, what role does each training method take in developing a humanoid robot? Reinforcement learning through digital twins in a virtual environment is difficult to implement and computationally expensive, but it underpins most of the training for humanoid robots because it accelerates the training from motion capture and video capture training methods. Motion capture is useful for training on tasks that require fine motor skills. But, of course, the drawback is that it requires a motion capture rig, and each task has to be taught to the robot by repeating it many times. That can be laborious, but how laborious depends on how sophisticated the AI models and reinforcement learning environment are. The better they are, the quicker the robot will be able to learn new skills. A robot with good AI models and reinforcement learning might need 10 to 20 motion capture examples of how to pick up a towel or hundreds of examples of how to fold a shirt. And, of course, if you want the robot to be able to fold a wide variety of clothing, it might need to be trained on different types of clothing and clothing materials. The ideal training method is to use video capture. That's because no motion capture equipment would be required, and it could eventually allow Optimus to learn tasks from any video example, such as YouTube content. That is, training with video data is highly scalable, which is essential for humanoid robots because they'll need to learn thousands of tasks. The drawback of training through video examples is that it requires the greatest degree of software sophistication. Instead of learning through direct motion sensor data to understand how to move, the robot has to infer how to move simply by processing the video data. In a sense, the robot has to develop a sense of self. But as Tesla recently showed with their breakthroughs in video training, it can be done and it's highly effective. Tesla's currently training Optimus using first-person videos, and they're looking to expand that to third-person videos from sources like YouTube, which is one step further in difficulty and sophistication, but also scalability. Lastly, supervised learning with labeled training data will enhance the robot's visual discernment, enabling it to tackle complex tasks like visual inspection and sorting or organizing parts. The drawback is that it requires humans to label potentially thousands of objects, or build an automated labeling system to do that. Luckily, Tesla's already built automated labeling systems for their self-driving project that could be used to label data for Optimus. As a final note on training, the ultimate way to train Optimus will be to give it such powerful AI that it can train itself exactly the way that humans train themselves, through practice and play. The ultimate training ground is reality, and any virtual environment is a cheap imitation. Virtual environments are currently necessary for training because the AI is dumb, requiring thousands of iterations to learn, which would destroy the robot and take months or years. Additionally, humanoid robots only currently number in the hundreds. If the robots were genuinely intelligent and there were millions of them, each robot could learn and practice skills, and add that knowledge to the collective intelligence of the robot fleet. So if one robot learned a specific task, then all of them would gain that ability. The ability to self-train in the real world and learn as a fleet seems like it would be years away, but it could happen sooner. The speed of advancement for humanoid robots is surprising even people in the industry, and often by several years. With all that in mind, what's the current state of training for humanoid robots? How is it expected to develop over the next few years? And what does that mean for expanding production of humanoid robots? I'll focus on Tesla here, but many of the current leading robotics companies are at a similar stage of research and development. To be clear, that doesn't mean they're all equal in terms of sophistication, but rather that they're working on similar challenges and solutions. In the past few years, most of Tesla's work on Optimus was still in the research phase. They were bringing together the basic building blocks of a brain for Optimus. With that groundwork in place, Optimus can now perceive, navigate, walk, manipulate objects, and understand basic commands, but it still has a relatively limited skill set, and it can look somewhat clumsy when performing those skills. Optimus has been doing useful work in Tesla's factories, but the primary goal of those robots was to gather real-world data and refine and accelerate their training feedback loop. And we're seeing the results of that now with Tesla's recent breakthroughs. Optimus is increasingly trainable. Tesla's providing it with large amounts of first-person data and doing reinforcement learning across a range of tasks, and of course having some fun and pushing its limits by teaching it to dance. That is, the base functionality is now there for Tesla to easily train and deploy Optimus as a useful product, which means it's time to start scaling the hardware and putting them to work in earnest. And Elon has indicated as much, saying that Tesla should have thousands of Optimus robots produced by the end of the year. Putting the robot to work in factories at larger scale at the end of this year will further refine and accelerate their training feedback loop, and also, in my view, on the back end, give them a chance to expand the menu of domestic tasks that the robot can do before it starts being sent out for home use. Then, next year, Tesla's going to start selling Optimus to employees. By then, my guess is that Tesla will likely have trained Optimus on hundreds of domestic tasks and made breakthroughs in training with third-person video data. That's not to mention that by the end of next year, Tesla will probably have developed the second generation or version of Optimus. That version will hopefully have fewer pinch points and therefore be safer for home use. Either way, the employees that buy Optimus will serve as another flywheel for training data. Once people have the robot in their homes, Tesla's going to find that the hundreds of tasks and commands that they've trained Optimus on needs to be thousands. After further training and refinement of the hardware and software, in 2027 or 2028, Tesla could start selling Optimus robots on a limited basis to the public, leveraging early adopters that are willing to pay a large premium and provide a lot of feedback and/or training, which is exactly what Tesla did with full self-driving for their vehicles. As a result, Optimus will quickly develop a large skill set and will increasingly be like working and interacting with a human. The more that's true, the larger the addressable market. And by 2028 or 2029, Optimus should be so useful and intuitive that it can be sold to the public in millions of units per year. On that note, some people have suggested that you'll be able to download skills for Optimus from some kind of app store. In my view, that's unlikely, because humanoid robots are driven by artificial intelligence, not programming. It won't take any special skills to train Optimus. It will just need to be shown examples of what to do. And there's billions of hours of internet video data out there just waiting to be tapped into. Optimus can then use that data to practice skills in a virtual environment or eventually in the real world. And once a skill is trained, it will be available to every robot in the fleet. So, unlike mobile phones where you have to pay to download an app to increase functionality, over time, Optimus will be able to perform any task within the boundaries of its hardware limits. It'll be a surreal, human-like companion that can do everything from playing the piano to reading bedtime stories to assisting with construction projects. But even if I'm incorrect, and there's a fee for certain high-value skills trained by some of the best experts in the world, it will certainly cost less for that training package than hiring the world expert. That is, Optimus won't just be going after labor that's considered unskilled, but also highly skilled labor. We'll get into the implications of that in the next video of the series. If you enjoyed this video, please consider supporting the channel by using the links in the description. Also, consider following me on X. I often use X as a testbed for sharing ideas, and X subscribers like my Patreon supporters generally get access to my videos a week early. On that note, a special thanks to my YouTube members, X-subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.